Hi guys, so here in this video we are going to analyze another important organic problem. So here we are going to synthesize X from Y through retrosynthetic approach. My request is that watch the video completely to get the best concept here on this problem. Okay, right. We know that retrosynthetic approach is very important nowadays in modern organic synthesis and also in competitive purpose. That's why it is very important to focus on retrosynthetic analysis and how it is going to help a student. So simply, if you have command on retrosynthetic approach, then it is easy to synthesize the product of any reaction. Okay, now here we can see how the retrosynthetic approach help us to produce X from the starting material or synthon Y. Okay, right. Now just look at the product here as in the case of a retrosynthetic approach. The product is having a 7-membered ring, right? The 7-membered ring should be converted to 6-membered ring. Okay, so what is the best reaction can be seen to convert this 6-membered ring into this 7-membered ring? The well-known rearrangement here we can use pinnacle rearrangement. Okay, so here is the OH and here is the OH. Okay, so this is the retrosynthetic step. Now what need to do? Here we have diol. The functional group inversion should be takes place. Okay, so here the diol is converted to alkene. Okay, right. In the next step, the famous reagent, that is Wittig reagent, should be applied. So simply the cleavage takes place here. Okay, right. Now double bond and O. So this is the starting material X, and if you know this retrosynthetic approach, then it is possible to produce X from reverse steps from here to here. Okay, so here we need to say Y, that is the synthon Y. Okay, right. Now we can start here from the starting material, or we can say synthon. So just let me know. Here we need to protect this carbonyl group. Do you know why? Because this carbonyl group is unconjugated, whereas this carbonyl group is conjugated. So the unconjugated carbonyl group is more reactive than conjugated carbonyl group. So this unconjugated carbonyl group can react with Wittig reagent, which will be used in the further steps in the way of synthesizing X. So we need to protect this more reactive unconjugated carbonyl group. Okay, right. Now take the, so simply acylation takes place, or what we say acetal formation takes place by just applying the glycol. Right. In the next step of the reaction, what happens? just apply the Wittig reagent, triphenyl paspene. Here is the negative charge and here is the positive charge. Okay, so when you apply Wittig reagent, now the free conjugated carbonyl group reacts with this Wittig reagent and produces its product. So here is the double bond. Okay, and here just write down that protected carbonyl group. Now we need to convert this alkene into diol. So that is the functional group inversion which we have seen in a retrosynthetic approach. Okay, so when you apply osmium tetroxide pyridine, now here is the formation of diol. Okay, in the next step, by just applying a base, that is pyridine, and followed by tosyl chloride. So pyridine abstract this proton, and here is the formation of negative charge on oxygen. This negative charge on oxygen going to attack on tosyl chloride by the elimination of Cl. Okay, so it produces the next step of the product where tosylation of hydroxy group takes place. Here O tosyl group. Okay, so here is the protected carbonyl group is there. Now in the next step, by just applying the weak Lewis acid, okay, weak Lewis acid, so simply pinochle rearrangement takes place. So try to check the mechanism of pinochle rearrangement. In this step, what happens? So the cleavage, that means the in the first step, the most reactive leaving group is tosyl group can be cleaved. Here is a formation of positive charge. So this positive charge should be compensated. In that case, the bond cleavage between oxygen and hydroxy group, and here is the formation of carbonyl group. Now the ring should cleave. The ring bond should cleave to attack this carbocation. Now here the double bonded carbon sp2 carbon cleaves to attack on this carbocation, and it is going to produce the final product X. Okay, here is the question: why this sp3 carbon is going? Why not this sp3 carbon is going to attack on this carbocation in the pinochle arrangement? Simply sp2 carbon moves in priority when we compared with that sp3 carbon. Okay, and in the next question you may get the question here: why the tosylation takes place on this terminal hydroxy group, why not on this ring hydroxy group? The answer is whenever whenever the tosylation takes place on this hydroxy group, now this is the leaving group, best leaving group. So whenever it cleaves from it, then the methyl group should move here. Okay, methyl group should move here. That means here is a formation of aldehyde. When we compare with the simple methyl group migration, the ring migration is preferred. Okay, so just note this point. Ring migration is preferred over simple methyl migration. So that's why. So tosylation takes place on this terminal hydroxy group, and it follow pinochle rearrangement and produces the final product X. Okay, right. So if you get any doubts, you can ask us. Thank you very much.